Hello, my name is Asad Mahmood Hassan, and today I am here to present my semester project, which is design and simulate a grid-connected PV system for MAN engineering building. As we know, global population is increasing day by day, and energy demand is also increasing accordingly. So energy prices are also going up significantly. So in this scenario, solar photovoltaic energy is a reliable solution to power up small utilities and facilities load. By producing solar energy from sunlight, we are not only producing green energy but also demonstrating our commitment for environmental management and innovation. In this project, we have designed a solar PV system for Memorial University Engineering Department building. We have designed only for the lighting and small power load of the building. So we have tried to make the system reliable and cost effective to achieve the environmental and economical goals. As far as the project site introduction is concerned, the project site is located in the city of St. John's, which is the which is the capital of province Newfoundland and Labrador. Our project building is situated in the Memorial University. It is engineering department building. So the solar resource available at the project site is around 3.15 kilowatt hour per meter square per day, and the annual temperature is around 4.88 centigrade. So the MAN facility management department has provided the load data, which is around 3.62 million kilowatt hour per year. So we have calculated all the data for uh, monthly, daily, and hourly on the basis of provided data from the facility management. So the site roof area is around 10,000 meters square, which we have calculated from the Google map. So for system designing, we have taken the following steps. We have determined the total load of the building according to load demand data, which is provided from the facility management department of the Memorial University. We have designed the system using available site resources and load the data using Homer Pro software. So we have truly studied the technical specification and related standards for the proposed equipment or materials used at site. So we have a steady state modeling and analysis of the complete system through MATLAB, and dynamic modeling and analysis of the complete system through MATLAB as well. Uh, we have designed a control and protection system to ensure robust operation through the MATLAB software. In this slide, you can see solar resource data at project site. As you can observe, from May to August, we have more than 4 kilowatt hour per meter square per day. The maximum radiance in the month of June, and the minimum in the month of December. So the average annual irradiance for St. John's is about 3.1 kilowatt hour per meter square per day, which is quite enough for our system to generate electricity for our building project. For load calculation of the engineering building, as I have mentioned earlier, we have received load demand data from the facility management department of the Memorial University, which shows that during the year 2022, the annual load was 3.62 million kilowatt hour. So, according to this load, we have calculated further per month, per day, and per hour calculations. And the area of the building roof is around 10,000 kilowatt, where we are going to install our solar panels. So we are in this project, we are only considering lighting and small power load. Please note that we are not including the heating load, which is around equal to the lighting and small power load. So as we have we don't have enough space on the roof to install the solar panels, so we can only be able to design a system for the lighting and small power of the building. Here we have daily load profile in the Homer Pro. So we can see here during the daytime, when the institutional activities are going on, we have the maximum load, which is around 750 kilowatt, and during the night time it is around 200 kilowatt. And in the seasonal profile, you can see Homer Pro gives us the data for all the months during a year. So we have 10,060 kilowatt hour per day. So now I would like to invite my project fellow, Mr. Wasim Ajaz, to continue the presentation. Thank you so much.
Okay, thank you, Asad, for letting me speak further and giving the presentation from here onward. So, okay, so as you can see in the schematic diagram, we have two sources of energy. One is the grid and the other one is the solar panels. And the power, the DC current which is produced by the solar panel is converted with an inverter. Uh, and then the energy is feed into the electric load or the building. So the approximate load for what we get to know from the university is 10,060 kilowatt hour per day is the load that is required for each day. So it need to be produced either by the solar panels or with the grid. So moving on to next slide. So once we run the simulation on the Homer, we for the PV panels, the we use the Homer optimization. The rated capacity of the panel is 1782 kilowatt, and the maximum power we will be getting out of the solar panel is 1723 kilowatt, and the solar penetration is around 54.2 kilowatt. So this is it for the power system output. Okay, so for the inverter, if you can see here that the total capacity of the inverter is like 715 kilowatt, and same is for the rectifier, but we are not going to use the rectifier as we are not using the batteries in our system. And the mean output of the inverter is 177 kilowatt. And here we can see that for the total annual generation of uh, the system, the 47.1% of the energy is produced from the solar panel, and 52.9% of the energy is purchased from the grid or the local power supplier. And the excess electricity is very negligible, is around 8.19% of uh, the installed capacity, and the renewable fraction of the solar system is 40.9%. So if you can see below that the solar energy is more in the month of June, July, and August, starting from April. So the reason for that is because we have more solar irradiance in these months, especially in St. John's. In this slide, we can see the optimization result for the Homer, and the first option with the Homer optimization is in which the energy is being consumed from both the sources, the solar and the grid, and it would be the cheapest option to be used for a hybrid system in which the total cost would be around 6.28 million, and if we only go with the grid system it will be 7.12 million dollars. So it's also a feasible system to be installed. And here in this slide we can see the renewable penetration of the solar system, and as we have discussed before also, that the total renewable production of the system divided by the total generation is around 47.1%, and the total renewable production with reference to the total by the load is 52.5%. So it's almost the half of the energy will be produced from the solar system. In this slide we can see that we have we have the MATLAB simulation of the system we have designed. For the solar panel we have considered like 25 degrees Celsius for the temperature and 1000 watt per meter square for the solar panel irradiance. And if you see with the solar panel block on the right upper side, we have the MPPT installed. MPPT signal is being sent, in which is taking the voltage and current, and then it's calculating the maximum power point tracking for the solar current which is produced. And for the MPPT we are using the incremental conductance. In next slide I will explain you that in a bit detail. And if you see that after MPPT the output signal is fed into MOSFET gate input, like with the input from the MPPT it will just control the current we can get from the solar panel just to maintain the maximum current from the solar panel. Then this signal is fed into the DC signal is fed into the inverter, and in inverter we are using with the PLL loop control. So it's just comparing the frequencies of the grid load and inverter load, and it's just synchronizing both the things. I will just explain that in the next slide also. Then after that we have used the LCL filter, and the load is connected with it. So here we can see the MPPT we are using, which is incremental conductance, and the logic behind incremental conductance is that it can stay constant at specific voltage on which it achieves its MPPT, but we can't compare it with the PO and O algorithm because P and O is not constant, and voltage kind of fluctuates compared to the incremental conductance. That is why we have used the incremental conductance here. So here we have two things, the inverter current and the voltage from the grid. So we are changing it from the ABC to DQ frame, and because in DQ we have two axes, x-axis and y-axis, so we have ID and IQ. Similarly for the grid we have the VD and VQ, and we are getting the omega t, the frequency from the grid. Excuse me. So below we can see that the comparison is being made with between ID and 240, and then the input is given into the PI controller, and then the output is again fed into the is again converted from DQ to the ABC. So same is for the IQs. The comparison is between made with the zero, and the PI controller is used for the feedback control, and the output is again put into the change back into ABC. So then we have a PWM generator here, and then the output from this is the pulse wave modulation, which is fed into the inverter. Here in this slide you can see the power, the load, the power generated from the photovoltaic cell and the grid. So here you can see that the power generated from the photovoltaic cell is also varying, and the power generated by the grid is also varying, but the power that is given to the load or supplied to the load is constant. So that means that our PLL loop is working fine. In this graph we have the power output of the inverter, and we can see that is a perfect sinusoidal wave with 320 volt is the peak to peak, and if we say what would be the RMS, it should be around like 208 to 210 volts. So the output of the inverter is perfect. And in this slide we have the current output of the inverter, so we can see that the is also perfect, and the maximum output is like 400 ampere, around 400 ampere for the load. So the conclusion is that with the MATLAB simulation the system is working perfectly. So in the end, the conclusion for the complete work we have done for the project for this renewable is that the if we add the solar system for the engineering building along with the grid system, it will work perfectly. It is feasible, is economically feasible, and it will be having a less carbon footprint. That's also the policy of the Canadian government as and also for the university to reduce our carbon footprint. So after that we have done the modeling and the feasibility of the system in Homer, which we also showed you in the presentation. And lastly, that the system performance is also simulated in MATLAB Simulink, and we can see that the operation and the robustness of the system is good. So it is a feasible project which can be implemented in the engineering building. And thank you for your time and listening to our presentation.